All right. Um, for today, we'll probably finish the chapter. We're going to go over uh, pretty much just two big examples of the conservation of energy, kind of to get everyone in the feel of how you can do these problems. In your book, there are like 12 different types of examples. So if you want more of a different variety, I'd say go over there and check those out. Uh, Along with, all the YouTube and other resources, there's going to be plenty of stuff on anything conservation of energy. Right now, we're just at the bit, or yesterday in class, I just finished talking about what potential energy was, sort of the arrangement of whatever uh, you're working on or looking at for the moment. So if something was, near another mass, that is gravitational potential energy. If there's some sort of spring that is compressed, it has elastic potential energy. There are these types of energy that is just stored within the object itself, sort of its potential to sort of be used in any sort of way. What is the relationship between kinetic energy and potential energy, though? I think yesterday I did an example that I just sort of like reasoned out maybe how they're related to one another. Today I'll show you a bit more thoroughly. So how are kinetic energy and potential energy related to each other? What's the relationship there? Well, we're going to first look at what type of work is being done on the system. So a while back, we've learned that just work, the total work is just the change in kinetic energy. Well, let's, start with the work equation and work from there. We start with the total work done. Yeah. So let's start with a system that's, it's everything that's possible. So when I say a work total right here, I mean, if I'm looking at a problem of, problem says this block is, being pushed on some surface. So I'm, drawing my sphere around this system, and I'm looking at every single thing that could possibly happen within this sphere of, possibility. So all of the total work that will be possible. So that's just the all of the work that is being influenced outside of what we are offering. So I'm going to say work external. So this is something like I throw a ball in the air and there is some it starts raining or something. It's work that is not from my doing, it's external, that's happening on the system, this sphere that I'm looking at. Okay, so there's that. Then there's me adding in the non-conservative work, conservative this is similar to the rain example, but imagine I also factor in the air resistance of me. I throw the ball through the air and it's windy as a constant breeze that is non-conservative. It's just taking the work that I put in and it's using it up non-conservatively. This is, I think I showed this with my diagram yesterday. And finally, we're going to add in the conservative work. This is the stuff that we can account for. We can say, I put this amount in to the system. I threw the ball with this speed. I threw it at that angle. I am standing here at a certain height. So this is the stuff I can account for. I put this stuff in. I'm expecting this stuff to come back to me. The same amount. So I'm going to just rearrange this equation a bit to make it easier for the next couple of steps. We're going to say the work external plus the non-conservative work is equal to the work total minus the work that is conservative, sorry. Okay, I'm going to then, right at the top of me talking about this, I said we have already learned that work, the equation for work, shows us a relationship to kinetic energy. Ooh, just barely. So we have a way to bring in kinetic energy to this system, and something I might have glossed over last lecture. There's just too many steps I didn't feel I properly got to. There's a way to show the potential energy is a conservative type of work. Let me write that out more in full right here. So we have the total energy. The total work is equal to the change of kinetic energy of the system. And we also know that's the negative work. So this is the work that is done by the system. The conservative work is the change in potential energy. May not have formally gotten to that in yesterday's class, but I think I covered a lot of what you needed for yesterday's class. We have this, these two forms now we can input into this equation. I'm going to just sort of put those in, replace them. We have an external force, an external work, a non-conservative work is equal to some sort of change in kinetic energy in the system plus change in potential energy of a system. And basically, I'm going to, again, sort of cut to the point of this is I'm going to say that this will eventually lead to showing that the potential energy and kinetic energy can be viewed in two forms. There's this external and this sort of, we had total, let me do up here. We had total and conservative on the right. So looking at just the system itself, we could say that's for something that is completely conserved, like this, and there is nothing on the left-hand side, we could say that the potential energy, or we could say that the total energy before equals the total energy after a sort of interaction, or maybe we take a situation where the energy might be transferred into another form or type. We could always say that the initial energy will equal the final energy. This is essentially, let me go like this. The change in kinetic energy of a system, the change in potential energy of a system. This is really this is a capital K. I'm just sort of grouping these together, and it's just saying energy before is energy after, is what this is saying. And we get a sort of definition for total mechanical energy. We have mechanical energy. It's just E mech is equal to the kinetic energy of the system plus the potential energy of the system. And this is always going to be a constant value. So I could add up all of the individual pieces of potential energy. If there's a spring in the problem, I could put that as a potential energy. If there's a spring that is, raised up off the ground, then I have elastic potential and gravitational potential. There's a spring off the ground and it's moving. There is elastic, gravitational, and then there's also kinetic energy involved. So by finding this sort of total mechanical energy, I'm able to completely, again, like what I was saying earlier, draw like a big sphere around this system and say, I'm just going to count up all of the energy in this system. And a good way to sort of check this as we go along, I'm going to do a few examples. A good way to check this is to compare this total mechanical energy with any sort of other forces that come into the problem. I'm just going to put this equation right underneath it. So we have the external work is the change in mechanical energy, total mechanical energy, minus any non-conservative work. This equation is also important. This is the work energy theorem. So imagine if I do have that sphere around my system. I'm just looking at all of the energy that's inside. That's all that I worry about. And some non-conservative forces come into play. There's friction, or there's a steady breeze on our projectile. That's sort of our system. And that will be an external force. It provides an external work right here. And what it's saying is that external work is just how much energy did I have originally minus what type of work did that force supply. So projectile through the air. So I already have so much energy I offered to this projectile. And then it's minus the air resistance. And that will be the external work done. We'll kind of see how this is used in the upcoming examples. Okay. So we have our first example, which says that we are near the edge of the roof of a 12-meter tall building. We're going to kick a ball off of the edge with an initial speed of 16 meters per second at an angle of 60 degrees above horizontal. And we're neglecting air resistance for this problem. Let's draw a little diagram of what's happening. I don't have to be too perfect with the picture. It'll just help me see what's going on. So we're on a building. It's pretty tall. It's 12 meters. It's probably about a 4 or 5 story building. And we have this ball. We're going to kick off of the edge. It's going to go up at a 60-degree angle like that. Let's make a dotted line right here. And we're going to say that this angle is 60 degrees. And also, what might be easy is to call, we're going to call this point where the ball sits on the roof, we're going to call that 0. That's sort of our origin. That's our starting point. We could either call this 0, or we could call the ground down here 0. That's up to, whatever you want to do when you're working on the problem. The energy is going to be the same in either case. Okay, so there is 0. We're going to say that the building itself right here is just going to label as H, 12 meters. The ball is going to just fly through the air. Something like that. What do we want to know? We want to know a couple things. how high above the height of the building does the ball rise? So how high above the height? So we want to know this height right here. I'm putting a lot in this little area. I'm going to put the height. I'm going to put that over here. I'm going to say that's height. And let's actually call that H top. So that's sort of the top of the arc that the ball makes it to. How high above the height of the building does the ball rise? And what is the speed of the ball just before it hits the ground? We want to know final speed over here. We have initial velocity right there. I think we might need one more velocity. Let's put a velocity of how fast the ball is moving right at the top of the arc. So right at the top of the arc, it is just for that split second moving completely horizontally. And we're going to call that the velocity while it's at the top of the arc. All right, so we have kind of a picture with a lot of the information from the problem. We want to know height and we want to know velocity. First, let's start out with using that work energy theorem. This is really just this is sort of just like a check as you enter the problem before you put any values down. So I'm going to say that's work external equal to the change in mechanical energy minus any non-conservative work. So this is just saying, is there any friction in this problem? Is there anything affecting the ball after I kick it and after it falls? Does some external force change what happens to the ball? And remember what is included in this change of energy. So within the change of energy, we have the kinetic energy and we have potential energy. So is there anything outside of those two that affects the ball? And the problem neatly tells us that neglect air resistance. So we're going to say no. There's nothing else outside of the energy we already offer this projectile. So there's no external energy. There is, whatever energy we start out with, or change of energy minus 0, like that. This is final minus initial. So this is just saying that the final mechanical energy is equal to the initial mechanical energy. So that'd be final minus initial. I'll just add 1 to the other side. Okay, so this is, let me break this down just a bit more. This is just saying that the kinetic energy, try to make that look capital K, kinetic energy, final, plus the potential energy, final, is equal to kinetic energy initial plus potential energy initial. That's all it's saying. we want to find a height first. So let's find the height of the ball when it's up here at the top of this arc. Now we could do this beforehand. In some previous chapters, if we knew enough information, we could find the height of the ball. But maybe the problem, you could see, maybe the problem wouldn't give us, a piece that we would need to, find this using those kinematic equations. Maybe this problem could have just given us an energy and said find the height. That's also doable this way. So we have, let's like flesh this out a bit more even. Final and initial, I'm just going to write them out even more in full. This is initial over here. Okay. So I have the equations right underneath what they are. And now we can see that if it depends on where I label the origin. So I'm calling right here at the top of the roof, I'm calling that 0. 0 height at the top of the roof. What that means for my problem is that my initial height, my initial like frame is going to be that very instant right as the ball gets some velocity at this angle right here. So that is initial. And basically the final is we don't want the ball, we don't want the height when it's down here. We already know how tall the building is. We want to know, we're going to call this the initial and we're going to call this the final. The two scenarios that we're going to break this up into. Okay, so for the final, I'm going to expand this out a bit so it looks a little better. So for the final, if I'm calling this up here the final velocity, I'm just taking two pictures of what's happening. So you have 1/2 mv top squared plus mg y final. So it's going to be this h top. That's where we're going to actually be able to solve for the height above the building. That is equal to its initial state. Vi, that was already labeled Vi, and G, and I'm going to call this just Y sub I still. What is the initial height? Well, we're calling this 0. So that means this whole term goes to 0. Now I can solve just for the height of the height of this arc. Let me rearrange. I'm going to, subtract over. I'm going to divide out the mass. I'm going to divide this g over to the other side. And what I get is h top equal to okay. All right. Something that is still left out, we don't quite know at this point. We don't know what the velocity is of the ball when it's at the top of its arc. We don't know v top right here. We can find that easily though. We've already learned a bit about projectiles, how to break things up into x and y coordinates. So finding this isn't actually as bad as it looks. I'll just say like over here. V top, that's just the x coordinates of its initial velocity. Or I could say x, which is just the same as the magnitude vi times cosine theta. Like that. Okay. Okay, so we have this new term to put in. And we know its initial velocity and we know the angle. So we're just putting in something that we know into this term. And this whole thing becomes, well, I can reduce it a bit before I plug a lot of values in here. Let's go one more step. It becomes 1 minus cosine squared theta over 2g. Now I can maybe put some values in and it'll be a lot easier, process. So in order to get the best results, whenever you're using like your calculator, you want to try to reduce it so you don't have to input a huge equation into a calculator. A calculator, maybe you can miss a parenthesis sign, and that will change all of the order of operations. So you should try to always break down the equation as much as you can before putting any values in. And this whole thing is over. Okay. And finally, we have the height that this ball is able to be projected upward above the building is another 9.8 meters. All right, so that's pretty high up there. What's the next thing we want to solve for? We want to find what is the speed of the ball just before it hits the ground. Okay, so very similar sort of starting points. We're going to say final equals initial energy. Its initial energy was on the roof of the building, and I gave it some velocity. So let's first start with that equation of mechanical energy. I'm going to shrink this a bit. So finding the velocity, final velocity, we'll say 1/2 mv final squared plus mg y final is equal to 1/2 mg, mv I squared plus mg y initial. Okay, so we have the same sort of starting points as last time. So now, no, even now, its starting point, I'm still calling the top of the roof a height of 0. So this term right here, since because of that 0, goes away. And we're left with just all of this. And we know its final height, that's just going to be 12 meters down. So that's just a negative 12 meters. We know the mass of the ball, we know gravity, we know its initial velocity that we've given it. So we know everything in this thing that I've underlined right here. I can just solve directly for the final velocity. Let me skip a lot of steps. I'm just going to say the final velocity is a big square root. You see, it's squared. I'm going to have to square root everything. It's a big square root of initial velocity squared minus 2g y of f. So the final height. Okay. Putting everything in. Minus 2 times 981 meters per second squared. And this will be a negative 12 meters, since our origin is up and then the ball is going to go down farther than that. And this equals final velocity of 22 meters per second. All right. So maybe you could see from this equation also, if the height of the building was taller, well, let's look at the picture before this. So if the height of the building was taller, instead of 12 meters, say it was 120 meters, we could expect that the velocity of the ball right as it reaches the ground will be much greater because it would have been falling for a lot longer. So that's sort of our intuition on that. But if we look at the equation, So it's 16 minus and a minus 12. So that makes this a positive term. This would then be 120. We would have a much greater final velocity. So that sort of checks out. And we've done all of this, this entire problem just by looking at the energy of the system. So drawing a bubble around what we wanted to know or what we're looking at. We say all of the energy is still here within this bubble. So it has to go somewhere. Where's the energy going? At one point, it's potential energy. At one point, it's kinetic, and so forth. All right. Next example is pretty good. We have a 2 kilogram block on a frictionless horizontal surface. It compresses a spring with a spring constant of 500 newtons per meter by 20 centimeters. The spring is then released, pushing the block. The block slides up a frictionless incline of 45 degrees. How far does the block slide up the surface of the incline? So starting out, again, just sort of our pre-problem checklist. I can say, what is the external force, external work done, the total mechanical energy. Is there any non-conservative work being done on this system? Well, it always helps us out when a problem says frictionless. So frictionless, that's just, there is no work that is, brought up out of nowhere. So this will be 0. And this will also be 0. And what this is just showing is that we can say that the final energy is equal to the initial energy. Okay. Something I forgot to do even before this is I personally like to draw a picture before I even start a problem. So we have this, we have a block on a surface. The block is right here. Some mass, and it's connected to a spring. And the spring is currently compressed a certain amount. (20 centimeters). As the spring is released, the block is going to be pushed. So the block I expect to be pushed all the way up to this equilibrium point and then beyond. It's just going to slide on this frictionless surface. And then at some point, it's going to go up an incline. That is at an angle of 45 degrees. And what we want to know in this problem, right there. What we want to know in this problem is the block is, I expect it to go this way. It's going to slide up, 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 and eventually stop. So the block is eventually going to stop somewhere. And what we want to know is how far up the surface of the ramp does the block slide? Not necessarily the height that the block is raised to, but what is the distance along the ramp? Okay. And then from here, I'd go and look at the work and the energy. I'd say final equals initial. Okay, what is the initial situation? We always have to cut it up into a before and an after, and it's always up to us to decide where do we want to call uh, the initial and where do we want to call the final. As long as I say this, I know that this statement will always be true for anywhere along uh, sort of an object's motion or a problem that is given to you. So I'm going to say the initial case is right when the spring is compressed. The spring is compressed. It has some spring constant K. Right as it starts to move the block. So just that very first instant before it moves the block, actually. The block isn't moving for this first case. So all of the energy is stored in the spring. So we have an initial system. And let's just list out all of the things it can be. So we always say kinetic energy, kinetic energy, initial plus potential energy initial. And that's equal to, I'm just going to say that again, except now we know that there's two types of potential energy in this problem. There is spring or elastic potential, and there's also gravitational potential. Let's add up each of these in the initial states. So I'm going to take my first picture, my first look at this when the spring is sort of being held still and nothing's moving, and the block is just sitting here, compressing the spring. So there's no kinetic energy. There is some elastic potential energy. What was the equation for this? It was 1/2 kx squared. And it doesn't say that in the problem, but I'm going to say that the surface that we're sliding on, that is a height of 0. So we have no potential energy from no gravitational potential energy. Let's look at the final situation. So I'm free to take a picture wherever else as this block slides along this surface. I'm going to take a picture right when the block reaches its top position right here, right when it stops. So it gets flinged along the surface, then slides up frictionless, and right as it stops right at the top of the ramp. So it's not moving anymore. And I chose it because I don't want to have to factor in some movement. So I'm going to say right when it stops at the top. It's also its highest position. Final. So I'm going to just write this one down. Some kinetic energy final. The spring or elastic potential final. Okay, we have, while we're looking at this second picture, there is no movement, so no kinetic energy. There is no elastic potential because the spring has already been extended, and at this point, when the block is up here, the spring is at equilibrium, so that's 0. And potential energy from gravity. Now we could say there's some change. It went from a ground level and now it's being raised up. It's changing its orientation off of the ground. So I'll just be mg, we'll say h. All right. Now looking at the equation, I have just at the top right up here, I'm just going to set those two things equal to each other. And we have this spring potential is equal to the gravitational potential. mgh equals 1/2 spring constant x squared. This thing, let's arrange it to solve for the height. What is the height that's brought up at? The height is the spring constant, k, times how far the spring was initially compressed, squared over 2 mg. Doing all of this, we'd always have to remember the problem gave us the units have to mesh. So the problem gave us centimeters up here. We need to convert that, and we'd use that spring constant it gave us, and it looks like they already gave us kilograms for the mass, so that should be good. After we do that, we get a height of 0.51 meters. That's the height of how far directly up the block was raised. I don't really want to know that. I want to know its distance along the ramp. Well, the reason that we solved for the height is now we have this really nice triangle that we can solve for. Let me just look at the ramp section now. Okay. So we have that angle, and now we have a height. And we want to know the distance along the ramp. So, or I guess it would be, I'll just say it like this. Yeah. We want to know the hypotenuse of this triangle. We have an angle, we have one side. That's just pretty simple at this point. We know that sine of an angle is equal to opposites over hypotenuse. So we could say we could solve for this distance, and I don't think I addressed it. I'm just calling it S because nothing else is nothing else in that I know of is labeled S, so it's easy for me to pick out that this is different. So S equals the height over sine theta. At the very end, say that the distance the block travels up the ramp, so on the surface of the ramp, is equal to 0.72 meters. All right. So that is our second example. I think we'll just finish in time. We've got one more page. So we have this, very handy way of looking at this system, looking at how it's moving, looking at how it's arranged, and just sort of adding them together and saying that's the whole energy of this thing. I can predict almost anything about it now. But there's something with the smallest tangent I'm going to go on is, why do things, why does a spring want to go that way? My thing froze. So why does a spring go like this? Or hold on, I'll go like this. There we go. Why does a spring, like the one in this problem, return to its equilibrium position always? If I compress a spring, it wants to force it back to some sort of state, or if I pull a spring, it wants to return to the same sort of state again. And we've also said that if I, force it somewhere, it's going to have some potential energy, some elastic potential energy. So it seems like things just want to return to their equilibrium position. And that's pretty much the case. Let me bring up pictures. Potential and equilibrium. So say we have a pendulum or a spring, like the one from the previous example. And I give either of these a little bit of a push. Actually, before I even give them a push, I just drew 3 separate pictures for this pendulum up here. So like 1, 2, 3. So if I just took 3 separate pictures different times. Say I have these things and they're stationary. They'll be sitting at their equilibrium position. So if this pendulum isn't already going, you can expect it to be sort of just sitting here. It's just sort of a ball on a string, sort of the arm for like a clock or something. It's just sitting here A swing set just hangs straight down. And for a spring, this is a bit different. It depends on how the spring is made. It's going to be sitting at some length, some specific equilibrium length. And actually, for this sake of this problem, I'll say it's right here. The center of the mass, that's part of the system. So what if I give either of these two things a little push and I disturb them a little bit? So I take this pendulum and I pull it to one side a little bit and I let it go. So if I raise it up a bit, I can expect that the pendulum will want to return to this place. That seems natural. It's super intuitive. And if I raise the pendulum to the other side, it doesn't act any different. It wants to return to the same sort of middle place. And that's sort of the place where the potential energy is the lowest. Let's look at the spring example. We've done that a bit more than the pendulum. So if we have the equilibrium position here, we're just saying the center of the mass, and I compress the spring a bit, well, it's going to want to return to that position. I give it a stretch, it will want to return back to that position. We can make a graph of this sort of process. So we could graph the energy of the system. So we have a graph of potential energy as I move something just a little bit to the left or to the right. So we have up here at the top, we have potential energy. And this is just a little displacement. And if we can see that if I move something just a little bit, I give it just a little bit of a displacement, it will sort of roll down this bowl and it wants to return to this sort of lowest energy state. I'm going to call, 0 or its lowest state. This is called a stable equilibrium. And I can define a stable equilibrium as given a small displacement, the system will return to this original point. Okay, so displacement in one direction or the other, it's all just sort of directed backward to this equilibrium position. That's what we see with pendulums and springs. What about something that's not stable? Something that is unstable. What are some things we could think of as unstable? Well, something that I just came up with out of nowhere was, what if we had, maybe you guys seen the videos of like There's this guy who just balances things at weird angles. Like I've seen him balance a sewing table with an old sewing machine on it with like several other objects on top of it. And these objects aren't moving. And so they are technically in an equilibrium position. So what was something that was happening here? They were returning to a state and not moving anymore once they reach this equilibrium position. Yeah, I can add that to my little definition too. So not moving. So if I balance something, it's also not moving. This is a sort of technical equilibrium. It is an equilibrium, but it's an unstable equilibrium. So if I balance a coffee cup full of coffee on top of a broom and I just leave the room, this object, this system is not moving. It's in an equilibrium state, but it's unstable. I have the sort of graph of the energy right next to it. So if I give this system, this coffee cup on a broom, just sitting in the middle of your bedroom, if I give it just the slightest displacement, just the slightest bit, in one direction or another, will it return to this original point? No. So this is going to be this point right here. And if I give it the slightest push, it's going to not return to this position. It's going to speed up as it moves outward, falling over, spilling coffee all over your floor. So I'm going to say my definition for this, I'm going to say given a small displacement, the system will move away from this original point. And it was momentarily in this equilibrium. That doesn't mean it naturally wants to be there. Something that's you'll learn if you take 4B, I think you start out with thermodynamics. Things just naturally want to find the lowest energy possible. So things will always try to find some lower potential, lower equilibrium state. So if I leave my room with a coffee cup on a broom, it is an unstable, I forgot to put down here, unstable equilibrium. Okay, the last bit for today. We're just sort of, this is actually just sort of like a conclusion because we've covered most of what this is going to say. So conservation of energy is just energy's neither created nor destroyed. It's always going to equal how much is given to a system, or the amount that is given must be equal to the amount that has been taken out. So very basic. I'm just going to say I'm looking at a problem, whatever the problem is. Here's our free body diagram. We're doing forces or whatever. Our free body diagram. Whatever energy is put into the system, I'm just going to say, we'll say like whatever energy is brought into this zone, our bubble we're looking at, the energy that comes in is going to equal the energy that goes out. So energy is always just transferred from one thing to another. All right. That's just kind of a little conclusion on this, on the theme of this chapter. There are a few more things at the end. There's a couple more sections on mass and energy. If you want to learn a bit more about how mass and energy are related, I'd say check that out. At the sort of the beginning of the universe, there was just energy, a complete universe made out of energy. And then over time, there was sort of this clumping of energy in certain pockets. And it turned out that mass was created from energy. It's something that's Albert Einstein sort of arrived at, sort of made famous with E equals mc squared. That's energy is equal to mass times the speed of light squared. If you want to learn a bit more about that, I'd say check out this section. Is it? It's like section 4 or 5. Yeah. There is only so much energy in the universe. No more energy is put into the universe from its beginning. We don't quite know, all of the processes, but we do know that there's a finite amount of energy that was put into the universe. So in all of our, at-home experiments we're doing, we can easily say that's whatever energy we put into, this ball rolling on a ramp, we can expect the energy to come back out in some form or another. All right. And that is the end of the chapter. If you guys have any questions, you can always email me. I'm going to grade the quiz today, and I'll send out an exam. I'll send out an announcement for the exam on Tuesday. Make sure you guys finish the homework so you practice this stuff also. The stuff that I just covered is also going to be on the exam. So the homework should help you with studying for that. What else? I think that's it. So if you have any questions, let me know. Otherwise, see you guys later.